Assalamu alaikum wa rahmatullahi wa barakatuh. So we will continue our discussion on Gauss-Jordan method. Okay, Gauss-Jordan method. So we will see a problem. So in the last lecture we have seen one problem. So we will see another example, and after that I will give you an homework. You can practice it in your home. So the question is to solve the following set of equations by using Gauss-Jordan method. Okay, so for the exam I will be specifically giving you the method, so you have to solve it by using that method. So if you solve it by using another method, you will not get any marks. Okay, now I will write the equation. It's 2x1 plus x2 minus 3x3 is equal to 11. Now 4x1 minus 2x2 plus 3x3 is equal to 8. Now this is 2 minus 2x1 plus 2x2 minus x3 is equal to minus 6. So these are all the equations that you need to solve. So you have to solve these equations and you have to obtain what is the value of x1, x2 and x3. Okay, so we will see how to solve this. So before that I will write the augmented matrix answer. I will write the augmented matrix as, see, on the right hand side I can write 11, 8 and minus 6, and this will be like 2, 1 and minus 3. This is 4, minus 2 and 3. You can see the coefficients here. Okay, like this for x1, x2 and x3. The second equation you can see the coefficients 4, minus 1 and 3. Next is minus 2, then it is 2, this is minus 2, 2 and minus 1. Okay, and on the right hand side you can see it is 11, 8, minus 6. That's what I have written here. Okay, you can see that's what I have written here. Now this is the augmented matrix. Now what we want in Gauss-Jordan method as the answer, in Gauss-Jordan method, GD, Gauss-Jordan method I will call GD method. Okay, Gauss-Jordan. So in this method what you want, finally you want to convert the augmented matrix into something here, something here, something here, and all this should be 1 and this should be 0. Okay, this is the final condition you need. You need to convert the augmented matrix into this form. Okay, you have to convert into this form by using row operations. Okay, by using row operation. So this is what the Gauss-Jordan method. So we have to convert into identity matrix. Okay, one part to identity matrix. Now you know that let us consider another okay, we will continue our discussion on this problem. So I will rewrite this matrix again for our convenience. So it become 2, 4, minus 2, same thing I am writing, 1, minus 2, 2, then this minus 3, 3, minus 1, and it's 11, 8, minus 6. Okay, for your convenience I am just writing it again. This matrix I am writing again. Okay, you can see here. Okay, this is what I am writing again. Now I will do some row operation because I want, you see here, for I want in this form, basically I want to convert into a form. I told you 1, 1, 1, 0, 0, 0, 0, 0, 0, and here may be something here, something here, something here. Okay, now I want here 1. Okay, so that means I want to convert this element into 1. So how to convert this element into 1? I am going to convert this element into 1. You see, all other elements will not change. 4 minus 2 3. I will write the row 2 and row 3, minus 2 2 and minus 1 and minus 6. But I will convert my row 1 by multiplying my row 1 with 1 by 2. Okay, I will multiply with 1 by 2. So then this become, you see here that there is no change here. I will use black color for something which is not changing. Then this is minus 1 and minus 6. But you see this is going to change now. What is happening? I am going to multiply this with 1 by 2. So this become 1 and this become 1 by 2 and this become minus 3 by 2 and this become 11 by 2. So I got 1 here, right? You see I got 1 here. So this is the advantage by multiplying with minus 1. Now I am going to change. You see here that I have a 4 here. I don't want 4. You see, if I compare with this is 0 basically. So I want to convert this into to 0, and I have something else here. You see, this also I want to convert to 0. So this also I want to convert to 0. So for that I will be writing again. I am going to write it. I will not change anything from row 1. So row 1 will be same. Okay, 1 by 2 minus 3 by 2 and 11 by 2. There is no change, same. Now you see I am going to do some operations. I am going to change my row 2 by using this equation. That means I will subtract from row 2 minus 4 times row 1. That means for row 1 you can see this element is 1. So if I multiply that with 1 with 4, then become 4. Then if I subtract it from row 2, then it becomes 0. So you see here that it's nothing but your 4 minus, I am talking about the row 2. Now it's 4 minus, I am talking about this equation. So 4 minus 4 into 1, this becomes 0. So I get 0. Now the second part is minus 2 minus 4 into 1 by 2. This become how much? This become minus 4, right? So this become minus 4. Now the next is 3 minus minus 3 by 2 into 1 by 2. Okay, not 1 by 2. Okay, so it's 3 minus 4 times minus 3 by 2. This become how much? So this become, for this is 2, this is become 9, right? It's become 9. So this become 9. Similarly, this become 8 minus 4 into 11 by 2. So this become 8 minus it's 8 minus, so what is 8 minus, this become 8 minus 2 into 11. So it become minus 2 into 11 is 22. So it's become minus 14. Okay, so I will get here as minus 14. Next you see I am going to change my row 3, because for my row 3 I need to convert my row 3 also. So I want here 0. I told you I want here 0 for the row 3. So you see my row 1 is already converted now. So my row 1 is converted now. Now I am going to talk about row 3. It's going to convert. There is minus 2 here. So what I will do, row 3 I will be adding my row 3 plus 2 times row 1. So what will happen here now? So minus 2. So I will write with a different color to avoid the confusion. So it's become minus 2 plus 2 into 1. That become 0. So I got 0, right? Now 2 plus 2 into 1 by 2. So it become 3, right? So this become 3. Now minus 1 plus 2 into minus 3 by 2, this become minus 4, right? So this become minus 4. Now next is minus 6 plus 2 into 11 by 2, this become 5, right? So this become 5. So I have converted my row 1 and I have converted my row 2 and row 3, and I got here 0. You see, I got both of these elements. That means I got here 0 and I got here 0. Both become now 0. Now they are 0. So you see, I have converted this to, now I got both of them 0. Next, what is the procedure? Next, I want to touch on this guy. Okay, I want to make this 0. I want to make this 0. Now next I will make this 0. Next make this 0. Make it 0. So now I am going to touch on this guy. I will use a different color. You see, now I am going to touch on this element and I am going to convert this to 0. That means I want to convert to 0. So before that, I will write again the matrix that we have got. Okay, I will write it again. So I will write all this matrix again. So 1 by 2, 3 minus 3 by 2 and 11 by 2. Next 0 minus 4, 9 minus 14. Then this is 0, 3 minus 4 and 5. Okay, so I have written again. Now what is my procedure? According to my procedure, 1 1 1, this is 0 0 0 0 0 0, and here some elements are there. Okay, now I want to convert this guy to 0. That means I want to convert this to 0. Convert to 0. That's what my objective. So what I will do? Now I will convert this to 0. How? You see, there is no change for row 2 and row 3. So I will write it as such. So 0 minus 4, 9 minus 14, 0, 3 minus 4 and 5. But I will change my row 2, this row 1 as row 1. Okay, I will change my row 1. Row 1, at first I will change my row 1. I will change my row 2 also. Okay, I will change my row 2 also first. So I will first of all, so for making this, I will first change my row 2, because in the row 2 I need this as 1. This is 1. You see, this is 1. So I want to convert this guy to 1. So what I will do, I will change my row 2 by row 2 into minus 1 by 4. So if I multiply with minus 1 by 4, okay, I will use a different color. I will use a different color here. So row 2 into minus 1 by 4, that is our new row 2. So this becomes 0, this become 1, it's become minus 9 by 4. Okay, and this become 7 by 2. If you multiply this, you will get this like this. Now I am going to change this in the next step. Okay, that's why I am deleting from here. So I will change in the next step. So I will repeat here this one again. 1 by 2 minus 3 by 2 and 11 by 2. Now you see, I am going to change this by using some other operation. So I will repeat again. We will continue here. We will continue the next page. So first of all, I will write again 1 by 2 minus 3 by 2, and this is 11 by 2. So 0 1 minus 9 by 4 and 7 by 2. Okay, and this is 0, 3, minus 4 and 5. Okay, that's what we have written. Yeah, same thing. Now I am going to change this guy to 0. Change to 0. How? For changing to 0, I need a step here. Okay, other elements I will write as such. Okay, I will change this to 0, and I want to convert this also to 0, because convert to 0. So I need two operations, one on row 2, one on row 3. I need to convert row 3, and another operation I need on row 1, and there is no change for row 2. Row 2 I am not going to change, so I will write it first. Okay, and this is 7 by 2. Now I will write my operation on row 1. You see what I am going to do on row 1. So row 1 is nothing but row 1 minus half row 2. Okay, half row 2. That means row 1 minus half row 2. So the first it will become row 1 minus, I will write this here, each element. What is the first element of row 1? Sorry, this not this one. The first element of row 1 is 1. So 1 minus half of row 2, that is 1 actually. So there is no change here. This is 1. Now this is what I am going to explain here. Next, 1 minus half of row 2. Half of row 2 means what? Half of 1, not 1 actually, 1 by 2 minus half of row 2. Half of 1, that is equal to 0, right? So this becomes 0 now, right? Similarly, you can get this is row 1 is minus 3 by 2 minus half of row 2. Row 2 is minus 9 by 4. So you will get this answer as minus 3 by 8. Okay, similarly you will get the here 15 by 4. So that's it. Next I am going to change, you see now this is changed here. Okay, now I am going to change the third row. So you see here, this is row 3. Row 3 I will be changing like this, row 3 minus 3 times row 2. Why I am doing like this? Because I know row 2 element is 1 here, so I can make use of row 2 and make this 3 as 0. So I can use this idea. So this is first element is 0. 0 minus 3 times 0, that is equal to 0, no change. Now the second element is 3. 3 minus 3 times 1, that becomes 0. That's the beauty. You see here this step. Now minus 4 minus 3 times minus 9 by 4. So you will get it as 11 by 4. So this become 11 by 4. Okay, and this become 11 by 2. So you have changed the row 2 also, row 3 also. So you have got a new matrix. Now I will write this matrix again. Okay, this matrix, this one I will rewrite again. So this I will rewrite again. Okay, this become 1, 0, minus 3 by 8, then 15 by 4. This becomes 0, 1, minus 9 by 4, and this is 7 by 2. This is 0, 0, 11 by 4, and minus 11 by 2. So I got it. Now I am going to change my row 3. Okay, I am going to change my row 3 because I need something like 1, 1, 1, and this is 0, 0, this is 0, 0, 0, 0, and after that I need at other end it may be something else. Okay, so I want this guy, I want to make this convert to 1. So how to convert to 1? By multiplying with 4 by 11. If you multiply with 4 by 11, then it will be converted into 1. So this is, if you multiply the row 3 by row 3 into 4 by 11, okay, So it's become 0, 0. 4 by 11 means if you multiply with 4 by 11, this become 1. And if you multiply this guy, it's become minus 2. Okay. Next elements, there is no changes. There is no change for other elements. So it's 15 by 4. This is 0, 1, minus 9 by 4. And this is 7 by 2. There is no change. Okay. Now you see there are some issues. I want here 0 and here 0, but this matrix is in perfect condition. Now this part, the third row is perfect. There is no issue. But you see here other two, this guy is not 0, so I need to convert this into 0, and this guy also I need to convert to 0. So I will rewrite again, continue. Okay, we will rewrite again this matrix first. Okay, I will continue again. Here you see it's 0, 0, 1 and minus 2, and this is 1, 0, minus 3 by 8 and 15 by 4, 0, 1, minus 9 by 4 and 7 by 2. Now I am going to do some operations and I am going to convert these two. At first I will convert this guy. Okay, so I am going to write the matrix. There is no change here, 0, 0, 1, and there is no change here, nothing. Okay, nothing is there to change. You have already got the value of z. Now I am going to change the row 1. So row 1 I am going to change as row 1 plus, you see this is minus 3 by 8. So I will multiply my row 3 with 3 by 8 and add with my row 3. So it become, you see all these elements in the row 3 are 0 and the last element is only 1. So if I add with row 3, this become 1 and this becomes 0, and I multiply this row 1 is minus 3 by 8 plus 3 by 8 into, this is 3 by 8, okay, 3 by 8 into row 3 is 1, okay, so this becomes 0. So I got it 0 here. And what will happen to this element is become 15 by 4 plus 3 by 8 into 7 by 2. So you will get something here as I will check whether it is correct. You will get it as 3. Okay, you will get this element as 3. That's it. Okay, now you see I want to make this minus 9 by 4 so to 0. So I want to make this 0. So I will be using again row 3 operation. So row 2 will be changed as row 2 plus 9 by 4 into row 3. So this is my operation, 9 by 4 into row 3. So this one I will write as row 2 plus 9 by 4 into row 3. So there won't be any change for the other elements because in the row 3 these two are 0 basically. So there is no change. So this is 0, this is 1, and this become minus 9 by 4. The third element become this guy, minus 9 by 4 plus 1 into 9 by 4. This becomes 0. That's the beauty. Now what about this? That's become 7 by 2 plus minus 2. Okay, 9 by 4 into 1. I will write like this. That's better. This is into 1. So 9 by 4 into 9 by 4 into minus 2. So you will get this as minus 1. So you got it. So you have now identity matrix and you have got some b tilde. You have your b is changed. So what is my x? So from this I can write my solutions. My solutions are, I can write my solutions. X is equal to 3. You see, this is my x, this is my y, and this is my z. So my y is equal to minus 1 and my z equal to -2. So that is the solution. So this is the answer. Okay. So I hope this problem is clear to you, and that is nothing but the Gauss-Jordan method. So we have seen two problems now. So today we will discuss about the concept of linear independence and linear dependence. Okay, dependence. So we will by definition, basically you will be saying the vectors are linearly independent. So what is a vector? Actually, that inshallah we will talk to you later. So let us assume that there are some vectors. Let's say I am representing my vectors with v1, v2, v3, etc. up to vk. K is a vector. Okay, vk is a vector, v1 is a vector. So these are all vectors in a vector space basically. So I will come to this later. Vectors in a vector space. Okay, so let us consider the equation a1 into v1 plus a2 into v2 plus a3 into v3 so on plus ak into vk is equal to 0, and this is a 0 vector. Basically this is a 0 vector. Okay, 0 vector. So what is a vector and what is the concept of this vectorization, and all these things I will be discussing later. So now you assume that you have some vectors v1, v2, v3 up to vk. Okay, so this is a vector. Now the combination, the linear combination of these vectors, linear combination of these vectors can be written as some constant a1 into v1. Suppose this is equal to 0. So then we will say that if we are getting exactly 0, we can write the combination of these vectors. This means the combination, if we can write the combination as 0 for some a1, for some a1, a2, a3, a4, etc. up to ak, then we say that the vectors then v1, the vectors v2, etc. up to vk are linearly dependent. Okay, linearly dependent. Okay, that means if I can make the linear combination equal to 0 for some constants, that means a1, a2, a3 are some constants. So then we will say that they are linearly dependent. Else we will say if a1 v1 plus a2 v2 plus up to ak vk, if we cannot make it 0, then they are linearly independent. They are independent. If they are dependent, we can make it 0. Now I can consider this as the equation 1 and this is the equation 2. Now I can write if, that means this is known as the linear independent, and the other one, blue color, actually I am going to write it by blue color. This is linearly dependent. Okay, so we will see this concept in more detail. So let us consider the linear dependency or linearly dependent case. Okay, there actually I told you a1 into v1 plus a2 into v2 plus a3 into v3, where this a1, a2, a3 etc. up to ak into Vk. These are all some scalars, okay, scalars, and this V1, V2, V3 are vectors, okay. So this is equal to 0 in the case of linearly dependent. That means this will become 0. Then in linear dependent case, you can say, let's say if I want to write V1, we can write my V1 as minus of A2 into V2 plus A3 into V3, okay, A3 into V3 and so on, plus AK into Vk, right, and I can divide it by using A1. You see, similarly I can write my V2 as 1 by A2 into A1 V1 plus A3 V3 and so on, AK Vk. So if the vectors are linearly dependent, I can write one vector in terms of other. So that's the importance. That means that we can write here V1 in terms of V2, V3, etc. Similarly, here I can write, we can write V2 in terms of V1, V2, etc., Vk, like this, okay. So I can write one vector in terms of other. That is nothing but the linear dependent. So if the vectors V1, V2, V3, etc. are linearly dependent, then we can write one vector in terms of other. That means one is depending on another, okay, that's why. So that is the situation. Now we will see our equation. So see the example in Gauss-Jordan method. I have given one example, Gauss-Jordan method. So let us consider an example from there. We have seen that we have seen that the solution to the equation 2x1 plus x2 minus 3x3 is equal to 11, 4x1 minus 2x2 plus 3x3 is equal to 8, and 2x1 plus 2x2 minus x3 is equal to minus 6. Now I can write this equation in the vector form, okay. I can write this equation like this. This is x1, this is x2, this is x3, and here it's 11, 8, minus 6. I told you this is the vector form. Why it is a vector form? That's what we are going to discuss now. Then you will understand what is this vectors v1, v2, etc., and what is this scalar constant a1, a2, etc. Okay. Now we will write like this. So this is 2, 1, minus 3, right? 2, 1 and minus 3. 2, 1 and minus 3. This is 4, minus 2 and plus 3. Okay. Then this is 2, 2 and minus 3. Sorry, not minus 3, minus 1, right? Minus 1. Am I correct? Let me check it. 2, 1, minus 3, 4, minus 2, 3. Then 2, 2, minus 1, 11, 8 and 6. Now I am going to rewrite this equation. This is the vector form, like a into x is equal to b, right? And what is your x? Here x is a vector anyway, x1, x2, x3, and a is a matrix here, okay, and this is your b. Now I am going to rewrite this equation again. This is known as 2, 1, minus 3. I will just rewrite 1, 2, 1, minus 3, and 4, minus 2, 3, 4, minus 2, 3, and 2, 2, minus 1, 2, 2, minus 1 into x1, x2 and x3, which is equal to 11, 8 and minus 6, right? 11, 8 and minus 6. Okay. Now I can write, please listen carefully about this. I can write like this. Let's say this is 2, 4, 2. I am multiplying with x1 plus, okay, 2 for 2, because you see here in my equation, everything, this is all are having x1. So I can take the x1 out. So I can write this part as x1 into 2 for 2, right? Then I can write the second part. You see, the second part of this one, I can take my x2 is common, so I can write it's 1 minus 2 and plus 2, right? Plus 2 plus, then here you see what is common here. Here it is common, it is nothing but x3, so it is minus 3, 3 minus 1. So I can write like this, which is equal to 11, 8 and minus 6. So I can write like this. This is into x2 into 1 minus 2, 1 minus 2 and 2 plus x3 into minus 3, 3 and minus 1, which is equal to your 11, 8 minus 6. Now I can say that your scalar constant, if you compare with this equation, I have already told you this is something like, okay, x1 into, let's say this is v1. Okay, I will write with the black color itself. This is v1 plus x2 into v2 plus x3 into v3 is equal to 11, 8 minus 6. Okay, so this is what your equation. So what is your v1? Your v1 is this one, and this is your v2, and this is your v3. So this is in the vector form basically. So if these are, we should know that what is the situation for this v1, v2 and v3. Okay, and where is your solution? This is your solution actually. x1, x2 and x3 are your solution, and you have got that the solution for this equation as 3 minus 1 and 2. So 3 minus 1 and 2, then you will get this particular value. So what I want to tell you is that in Gauss-Jordan method, you have reduced the same equation. In Gauss-Jordan method, you have reduced the matrix into the form. You have reduced this matrix. Basically, you have reduced this matrix. You see here, the matrix was 2, 1 minus 3, then 4 minus 2, 3, then minus 2, right? Minus 2. It's minus 2 or plus 2? Let me check it. Okay, this is minus 2. So we have minus 2 here and minus 2 here. Okay, sorry for this. And this is minus 2, and this is 2 and minus 3. Okay, not minus 3, minus 1. It's minus 1, right? Yes, it's minus 1. And you are having this 11, 8 and minus 6. And finally, you converted this matrix. You converted this into which form? 1 0 0 0 1 0 0 0 1, and you are getting 3 minus 1 and minus 2, and finally you got the solution as x1 is equal to 3 and x2 is equal to minus 1 and x3 is equal to minus 2. Now here basically you can see here that this matrix, so if this is the solution, what I can write here from this, I can write here that x1 into 1 0 0 plus x2 into 0 1 0 plus x3 into 0 0 1, I will get the value 3 minus 1 and 2. You see here. So I will be getting this value. We will check it anyway. That means I can reduce this. I can write as, I write it as, you see, this is my x1. So 1 0 0, because you are actually reducing the same equation. So plus x2 into 0 0 1 0 plus x3 into 0 0 1, which you will get it as 3 minus 1 and minus 2. That's why, okay, you are getting like this. Now you see that you are getting the equation like this. Similarly, if you are using the same x1 for this equation, particularly this one, that means x1 into 2 4, this is the last form, okay, last form, and this is the original form. So x1 into 2 4 minus 2 plus x2 into 1 minus 2 2 plus x3 into minus 3 3 1, this is equal to minus 3 minus 1, it's equal to 1186, okay. And you put the same value for x1, x2, x3. And what is the answer for x1, x2, x3? 3 minus 1 and minus 2. So you put here 3, you put here minus 1 and minus 2, right? And here also you put here 3, minus 1 and minus 2. Let us consider V1 is equal to 1 0 0 and V2 is equal to 0 1 0 and V3 is equal to 0 0 1. I cannot write V1 in terms of V2 and V3. I cannot write V1 is equal to some constant, let's say C1 into V2 plus C3 into V3. I cannot write like this. This is not equal to, okay, that means this is not possible. Why? Because for V1 you can see that the element 1 is on the top, and here for V2 this is 0, and for V3 this is 0. So this is 0, this is 0, and this is 1 here. So because of this reason I cannot write one vector in terms of another. And basically you see here that there are 3 independent vectors. That means here if you take V1, V2 and V3, all are independent. All are independent. Okay. So why we are getting this independence? You see here in the row echelon form that we have used in Gauss-Jordan method, that is, you are getting 1 0 0 0 1 0 0 0 1, and this is 3 minus 1 and minus 2, and this is not 0. This is not all 0. It is not all 0. It is not all 0. This is not all 0. That's why. If it is all 0, it will be linearly dependent only. So you can see here that whatever you are seeing for this matrix A, this is the matrix A, and this matrix A has been reduced to 0 0 1 0 0 1. A has been reduced like this, and it is a 3 by 3 matrix. Then we will say that there are 3 vectors. What are these 3 vectors? V1, V2 and V3 are linearly independent. That means they are independent. They are not depending on another. Okay, that means they are independent. That means we cannot write one vector in terms of another. So there are three linearly independent vectors. How many? There are three linearly independent, I can say Li, linearly independent vectors. And this number of, that means the number of linearly independent vectors, we will say it as the rank of A. And what is the rank of A? It is nothing but 3 in this case. So this is a full rank. Actually there are 3 equations and the rank of A is 3. So this is a full rank. So basically A is a 3 by 3 matrix here. Here actually A was a 3 by 3 matrix and the rank of A is also 3. So this is a full rank. We will say it is a full rank. That means it is having the rank same as that of its dimension. Okay, 3 by 3. So this is the concept of linearly dependent and linearly independent. So I hope it is clear to you, right? So inshallah we will see one more thing. Okay. So let us consider another example. So in our previous example, actually it is a full rank. That's why we have a unique solution. So if the matrix A is full rank, if A is full rank, that means if there are 3 unknowns and the rank of A is 3, that means if I can reduce my A as in the form that we have discussed before, then I can say that A is full rank. Okay, that means you will have all the elements here, but all this, suppose this is 0, then this is not full rank, I can say. Then this is not full rank, not full rank. Suppose this is a 3 by 3 and this is 0, so maximum you will get the rank as 2. So here rank of A is equal to 2. If A is full rank means what? Then it will be, you cannot reduce this completely into 0, all non-zero, non-zero, non-zero. So there won't be any vector. You will be getting something like, for example, you will be getting something like this maximum. This is fine. So this is a 3 by 3 and the rank is also 3. Now we will see another case with rank is not 3. So let us consider 2 equations. Okay, consider the equation 2x1 plus y minus, not y, it's x2, 2x1 plus x2 minus x3 is equal to 0. Then x1 plus 2x2 minus 2x3 is equal to 0. Then it is 4x1 plus 2x2 minus 2x3 is equal to 0. So I will not consider 0 first. I will give if it is 0, it is a homogeneous equation. So I will just give some another thing like this is 2, this is 3 and this is 4. Okay, this is 4. Now let us consider this equation. Now I can write this equation as 2, 1 and minus 3, and in Gaussian elimination method I will be using a form, and that form we will call it as a row reduced form or row echelon form. Row echelon form. So I am going to write it in row echelon form, means by row reduction techniques. Okay, that we have already discussed about the row reduction, how to convert some elements into 0, lower part into 0 like this. Okay, and this is 4, this is 1, this is 2, this is minus 2, this is 4, this is 2, this is minus 2. Now let us consider this is our A and this is our B, this is our augmented matrix. Now I am going to transform this matrix into another form by using row reduction. So this is 2, 1 minus 3 and 2, and this is 2, 1, 2 minus 2 and 3. Now I can write this as this row. I can write row 3 is equal to, I am going to write row 3 as row 3 minus 2 times row 2. So row 3 minus 2 times row 2 means 4 minus 2 into 2, that becomes 0. This becomes 0. Similarly, this also, I think I have made a mistake here. Yeah, this is minus 1. So minus 1, sorry. So what will happen here? This become also 0 and this also becomes 0. Now you see my matrix has become like this. Now I will rewrite it. So it is 2, 2, 1 minus 3. It's not minus 3, minus 1 here. Okay, minus 1. 2, 1 minus 1. 2, 1 minus 1, and this is 2, and this is 1, 2 minus 2, 1, 2 minus 2, and this is 3, and this is 0, 0, 0, 0. Now I will again reduce this, okay, because I will make this part as 0 here. This part I will make it 0. So what will happen here now? I will make this part as 0. Then you can see here that this become row 2 minus row 2. I will be changing as row 2 minus half row 1. Okay, half row 1. Is it clear? So 1 minus, so it become 1 minus half of 2. So this become 0. So this becomes 0. This is 2, this is 1, and this is minus 1, and this is 2. Okay. Now the second element, 2 minus half of 1, that become 1.5. So this become 1.5. Next is minus 2 minus half of minus 1. This become minus 1.5. Minus 1.5, right? Minus 1.5. Then this become the third element, 3 minus half of 2. So 3 minus half of 2, 3 minus 1 is 2. Okay, this become 2. And the other element 0, 0, 0. Okay, we will again try to reduce this. We will try, I will write it again. This become 2, 1 minus 1, 2. 2, 1 minus 1, 2. Then I am going to change my row 2 again. What I am going to do, row 2 is changed like row 2 divided by 1.5. Okay, I am going to divide it by 1.5. Then this becomes 0, this becomes 1, and this becomes minus 1. And other will be 0, 0, 0. Now I am going to subtract this I am going to let me okay. Okay, now is there any mistake? I just want to check it. So this is 2, 1 minus 1. Yeah. Okay, now we will see how can I reduce my this number. I will make it 0. So this become 2, this become R1 is R1 minus R2. So this become 2, and 1 minus 1 becomes 0, and minus 1 minus minus 1, that means it become again 0, and this is okay, I forgot to write it. So 2 divided by 1.5, actually this become 2 by 1.5. So 2 by 1.5 is 2 into 2 by 3, this become 4 by 3. So this become 4 by 3, and this is 0 anyway. So this is R1 minus R2. I am going to just write R1 minus R2. So this becomes 0. So 2 minus 4 by 3. 2 minus 4 by 3 is 6, minus 4 by 3 is 2 by 3. Okay. Next, this is 0, this is 1, this is minus 1, and this is 4 by 3. This is 0, 0, 0, and 0. I can write again this one after dividing my row 1 as row 1 by 2. So this becomes 1, 0, 0. This becomes 0, 1, minus 1, this is 0, 0, 0. And this becomes 1 by 3. This becomes 4 by 3, and this becomes 0. Now you see that I will rewrite this matrix. 1, 0, 0, and 1 by 3, and 4 by 3, and 0. This becomes 0, 1, minus 1, 0, 1, minus 1, and this is 0, 0, 0. Now you see here that your A is reduced like this. A is reduced to, this has become all 0 entries, you see, including this one as 0. So this has become all 0 entries, and number of non-zero rows are 2. That means there are 2 linearly independent equations or vectors, you can say. That means the rank of A is equal to 2, and the rank of A, which is equal to 2, but this is less than actually 3. Why it is less than 3? 3 means actual size of the matrix A is less than the actual size of the matrix A. So you can see that the third equation has become 0. That means it is having some relation with the other equations. Okay, that means that there are only 2 independent equations, and the third equation is basically, it is a the third equation, you can write it as a combination. So there are only 2 independent situations or 2 equations. If you take 2 equations, they are independent, but if you consider 3 equations, only 2 are independent, one is actually depending on another. That's why. But in the previous case, we have got the matrix, identity matrix, something like that, which is non-zero. So if we are getting a non-zero form, we can easily say that all equations are independent. So if the rank is, if it is full rank, we can say it is linearly independent, but here it is linearly dependent. Okay, it is not full rank, not full rank. So equations are linearly dependent. But how many equations are linearly dependent? Only 2 equations. But if I am considering all the 3 equations, they are linearly dependent. I can write one equation in terms of another. Okay, you can see here that my equations are reduced to this form. That means 1, 0, 0, and 1 by 3. This is 0, 1, minus 1, 4 by 3, right? 4 by 3, am I correct? Yes, 4 by 3. And another one, 0, 0, 0, 0, 0, 0. So what is the value of x1? x1 is equal to 1 by 3. And what is the second equation? What does this second equation tells us? The second equation tells us that x2 minus x3 is equal to 4 by 3. because if you write it in matrix form, you will get like this. So what is your x2? x2 is equal to x3 plus 4 by 3. And what does this equation tells that? This is 0. So this equation tells that 0x1 plus 0x2 plus 0x3 is equal to 0. And we have already the situation for x1 and x2, so we can omit this. So 0x3 is equal to 0. So x3 can be any value. So you can see here now that your x3 can be anything. That means your x2 can be anything. So you see your x3 can be anything and x2 can be anything, because x2 is equal to x3 plus 4 by 3. So x2 can be anything. So this can be anything, and x2 and x3 are depending on one another. But you see here that you can write here as the solution x1 is equal to 1 by 3, x2 is equal to x3 plus 4 by 3, and x3 can be anything. That means you can get any value for x2 also according to the value of x3. Okay. So how many solutions? If x1 is equal to 1 by 3 and x2 is, suppose x3 is equal to 0, you will get one solution. If x3 is equal to 1, you will get another solution. If x3 is equal to 2, and you will get another solution for x3, x2, etc. Okay, like this. So that means that this can be of infinite number of solutions. Okay. And also I told you that the rank of A is equal to 2. Rank of A is equal to 2. I will write it correctly. The rank of A is equal to 2. So here you see here that the rank of A is equal to 2, which is less than the size of A. What is the size of A? It was 3, right? That means 2 is less than 3. That means that basically if you check this, you will get your determinant equal to 0. So the matrix inversion is also not possible. So you will get the determinant of this A is equal to 0. If A is full rank, you will not get the determinant 0. So if A was full rank, you will not get determinant equal to 0. But in this case, you will get determinant equal to 0 because rank of A is less than its size basically. The size is actually 3 by 3. If I take the dimension 3, so rank of A is 2 now. So 2 is less than 3. So the determinant is also 0. Okay. So if A, suppose if A is not full rank, then the determinant of A will be equal to 0. That means it shows that there are some equations are linearly dependent. This shows that equations are linearly dependent. So in such case, we get many solutions, infinite number of solutions. Okay, this is the situation. Now we will see homogeneous systems. Okay, homogeneous systems of equation. So we will see the same example, but on the right hand side it will be equal to 0. So 2x1 minus 2x1 plus x2 minus x3 equal to 0. Now x1 plus 2x2 minus 2x3 is also equal to 0. Okay, this is now it's 4x1 plus 2x2 minus 2x3 is also equal to 0. So basically you can see by observation itself, you can see that if you multiply the equation number 1 with, if you multiply the equation 1 with 2, the number 2, then you will get the equation number 3 basically, right? That means it is linearly dependent. So we will see by reducing into the form. So it's 2 1 minus 1 and 0. This is 1 2 minus 2 and 0. This is 4 2 minus 2 and 0. So I can reduce into this form. I am not going to write all the steps. 1 0 0. This is 0 1 minus 1 and 0, and this is 0 0 0. Now how you can reduce like this? By using row operation. You know how to perform row operation. I have solved many problems, 4 or 5 problems. Okay, so row operations, we will get like this. We will get the above form. Okay, so I will rewrite it. So it's 1 0 0 0 1 minus 1 0 0, and you will get, I think last one is 0 0 0, right? 0 0 0, it's equal to 0, right? So this is our form, right? This is our form. Now this form is, you see here, from this x1 plus 0 x2 plus 0 x3, that means I am talking about the first row. This is equal to 0. That means that your x1 is equal to 0. Next is 0 x1 plus x2 minus x1 is equal to 0. This is from the second row. Okay, this is second equation, second row. That means row 1, let's say this row 1 and row 2, and this is row 3. So I can use the same convention here also. It's row 1 and row 2. Okay, this is equal to 0, means that x2 minus x1 is equal to 0. Not x2 minus x1, it's x2 minus x3 is equal to 0. So what is x2? x2 is equal to x3. So I got one solution here and here, but one is depending on another. Next is row 3, 0 x1 plus 0 x2 plus 0 x3 is equal to 0. So this means that we have already talked about x1, so omit here, and we have already talked about x2, so you can omit here. Now 0 x3 is equal to 0, so x3 can be any value, because so x3, this implies that x3 can be any value. So this means that you can change the value of x3. If you change the value of x3, x2 also will be any value. That means that you will get x1 equal to 0, x2 will be equal to x3, and x3 can be any value. Suppose x3 is equal to 1 is a solution, x3 is equal to 2 is also a solution, x3 is equal to 3 is also a solution, like this. So you will get x1 equal to 0, x2 is equal to x3, and x3 can be any value. Okay, that means that you will get infinite number of solution here, right? So even though it is an homogeneous equation, definitely x1 equal to 0, x2 is equal to 0, and x3 is equal to 0. Here you see that x2 is equal to x3 is also a solution. Similarly, okay, also we will see another thing. Also x1 equal to 0, x2 equal to 1, and x3 equal to 1 is also a solution. Like this it will continue. Okay, and that means you will get infinite number of solution. So this is the concept of linear independence. So whenever you are getting a matrix, to find linear, this is actually linearly dependent. That's why you are getting linearly dependent. That's why you are getting infinite number of solution. So if the equations are linearly independent, you will get only one solution. But if the equations are linearly dependent, then you will get many solution. And how to find this? To obtain to find whether it is linearly independent or dependent, first of all, you should have a matrix like this A. Let's say this is B1, B2 and B3. Okay. Now if you perform the row operation, then suppose you are getting a 0 here. Let's say we are considering only the matrix A, that's enough. Okay, that's A. So this is a matrix A. So you change your A row operation. After row operation, your matrix will be changed. Suppose you are getting some elements here, something non-zeros here. Non-zero means I am showing this non-zeros. Non-zero. This is also non-zeros. So I am just reducing like this, and I am getting here all 0 for one row. Then it's not full rank. That means you have many solution case. But if you are getting so if it is not full rank, that means that it is this case linearly dependent. Okay. But if A reduced to something like this, suppose this, fine, like this, for example, you see some non-zero, then this means that its A is full rank. That means that you have only one solution. Okay, so I hope this is clear to you. Method. So we have seen all the direct methods. So we have seen for solution of linear equation, we have seen for solution to set of linear equations by using the what was the first method? We have seen by using the Cramer's rule. Then we have seen another method, which is the matrix inversion. Then we have seen the Gauss elimination method. Then we have seen the Gauss-Jordan method. So these are the methods we have discussed, and all these methods are coming under direct methods. Okay, direct methods. So all these are coming under the direct methods, and you have seen that all these are direct methods. Now we have something known as the iterative methods also. Now we will see something known as iterative method. So we will see two methods here. Iterative is nothing but it's Jacobi iteration method. Okay, then it's nothing but Gauss-Seidel iteration. Okay, these are the two methods that we are going to discuss. So we finished about the Cramer's rule, matrix inversion, Gauss elimination and Gauss-Jordan. Now we have to finish the Jacobi iteration and Gauss-Seidel iteration. So we are going to discuss now the iterative method. Okay, so for solving it will like iteration. So you will be do the computation again and again. That means iteration means do the computation computation again and again. Okay, so basically you can easily program these kind of methods in the computer. So it can be easily programmed, it can be easily programmed in the computer. Okay, if you have a microcontroller also, you can do this. It's very easy. So this is what we are going to discuss. So first of all, we will be discussing the Jacobi's iteration method. Okay, there are two methods, and then the second, it's nothing but Gauss-Seidel iteration method. Okay, so first one we are going to discuss now, Jacobi's iteration. So Jacobi's iteration method. Okay, Jacobi's iteration method. So this method is having another name. This is also known as the method of simultaneous displacements. So simultaneously we will be solving for x, y and z. Okay, and after that again we will solve for x, y and z, and then again we will solve for x, y, z, and it is an iterative method. Okay, that's what we have seen now. So let us consider a set of linear equations. Let's say we have equation a11 into x1 plus a12 into x2 plus a13 into x3 plus, okay, let's see, that's enough. So this is equal to b1. Now a21 into x1 plus a22 into x2 plus a23 into x3 is equal to b2. Now a31 into x1 plus a32 into x2 plus a33 into x3 is equal to b3. So what I am going to do is that for solving these kind of equations, we have some conditions. If we want to solve by using this Jacobi iteration, we have some conditions. What are these conditions? The magnitude of a11 should be greater than a12, the magnitude of a12 plus magnitude of a13. So similarly, a22, the magnitude of a22 should be greater than a21 plus a23. Okay, and the third one, a33, should be greater than a31 plus a32. That means if you write it by using a matrix, this is your x1, this is your x2, and this is your x3. It's equal to b1, b2 and b3. Okay, now this is a11, a12, a13, a21, a22 and a23, a31, a32 and a33. So this number, what I am saying is that this number, the magnitude of this a11 should be greater than this magnitude a12 plus this magnitude a13. Okay, similarly you should consider this element. Okay, so this I am going to round it, and this, the second condition, this number, that means I will take this condition, the magnitude of a22 should be greater than the magnitude of a21 plus magnitude of a23. So what are these numbers? One is here and another is here. Okay, and the third one, you are focusing on this element. So magnitude of a33 should be greater than this number and this number. That means magnitude of these two numbers, a31 plus a32. Okay, that means your matrix should have large diagonal elements. Okay, basically. So how to solve this? So if these conditions are met, only then we will get the method will converge. So the method will converge, the method will converge to true solution only if the conditions above, that means these conditions, okay, I am talking about these conditions. So the conditions above are satisfied, otherwise you will not get a correct answer. So before proceeding, you have to first check this condition whether it is okay for your problem. Now I will rewrite the equations. A11 into x1 plus a12 into x2 plus a13 into x3 is equal to b1. A22 into x1 plus, sorry, not a22, a21 into x1 plus a22 into x2 plus a23 into x3 is equal to b2. A31 into x1 plus a32 into x2 plus a33 into x3 is equal to b3. So what is my x1? My x1 is equal to b1. I can write by using this first equation. So by using this equation, I can write a11 into x1 is equal to b1 minus a12 into x2 plus a13 into x3. Am I correct? Yes. Now x1 can be written as, you have this term b1 minus a12 into x2 plus a13 into x3, right? And you can divide it by a11, right? So this is your x1. Now you can write your x2 in the same way. You can write your x2, you can write this x2. x2 is equal to b2 minus a21 into x1 minus a23 into x3, and you have to divide by a22, okay, just by solving the second equation. Now that's it, okay. Now you can write your third thing, that means you can focus here. So I can write my x3 is equal to b3 minus a31 into x1 minus a32 into x2 into 1 by a33. So that's it. So you got everything, right? Now this is how you can first find. So you will first find x1, then find x2, then find x3, okay, and after that you will use x1, x2, x3 from the previous iteration and you will proceed, okay. So I will first we will solve a problem, then it will be very easy for you to understand, okay. Now let us see a problem. Solve, this is an example. Solve the following equations by Jacobi's method, okay, Jacobi's iteration or Jacobi's method. What is the equation? 15x1 plus 3x2 minus 2x3 is equal to 85, and this is 2x1 plus 10x2 plus x3 is equal to 51, and this is x1 minus 2x2 plus 8x3 is equal to 5, okay. Now let me check again. 15, 3 minus 2, 2, 10, 1, then 1 minus 2, 8, okay, 85, 51. So this is the equation. So first I am going to solve this. So we will check the condition first. We will check the condition. You see here, I will take this equation, and from this I will check this number. So it's magnitude of 15, whether it is greater than magnitude of 3 plus magnitude of 2. So this is become 5. So the magnitude of 15 is greater than 5, right? Or 15 is greater than 5, you can say 15 is greater than 5. So this condition is okay. Next I will check another condition, okay, about this one. So the second equation, so I will check the condition. So magnitude of 10 is greater than the magnitude of, this is 2 plus this magnitude is 1, okay. So 10 is greater than 3, okay, fine. Now next condition I will check about this guy, okay. So the magnitude of 8, whether it is greater than, this magnitude is magnitude of 1 and this magnitude is minus 2, so magnitude of minus 2. So 8 is greater than 1 plus 2, it's 3, okay. This is also satisfied. So all the conditions are okay now, okay, all the conditions are okay. So all conditions are satisfied. So we can proceed, we will get an answer. Otherwise, if these conditions are not satisfied, we will not get an answer properly. You have to do many times, but even though sometimes it will not converge. So we can proceed to obtain solution. So what I am going to do with this equation, so I will rewrite the equation first, okay. I will again write the equations. So what was rewrite the equations first. So what is that? 15x1 plus 3x2 minus 2x3 is equal to 85. Now 2x1 plus 10x2 plus x3 is equal to 51. Then x1 minus 2x2 plus 8x3 is equal to 5. Let me check again. Okay, 15, 3 minus 2, 15, 3 minus 2. Next is 2, 10, 1, 2, 10, 1. Then 1 minus 2, 8, 1 minus 2, 8, and 85, 51, 5. Okay, this is my equation. So from this equation, I am going to find my x1. What is my x1? x1 is nothing but 85 minus 3x2 minus 2x3, and you just divide it with 1 by 15 or multiply with 1 by 15. So you will get this, okay. Next you will find, so this is your x1, okay, this is your x1. Next you will find your x2 from this. So what is that x2? You will find x2 from this. So x2 is equal to, you have 51 on the right side minus 2x1 minus x3, then you will divide it with 10, that means multiply with 1 by 10. Next is you have something from here, that is x3. You can find, this is 5 minus x1, okay, then plus 2x2, okay, then you will divide it with 8, that means into 1 by 8. So this is just solving the equation simply. Now we are going to draw a table. This is, now we are going to draw a table. So initially we assume that, this is an assumption, x1 equal to 0, x2 equal to 0, and x3 equal to 0. Then iteratively we will proceed. So we are going to proceed iteratively, okay, iteratively. So what is my x1, x2, okay, x2 and x3. I am going to write these equations. It is 1 by 15 into 85 minus 3x2 minus, is minus or no, it's not minus. If I move this become plus. So plus, sorry, plus 2x3. Okay, this is the first. Now what is my x2? It's 1 by 10 into 51 minus 2x1 minus x3. Okay, that's it. And what is my x3? It is 1 by 8 into 5 minus x1 plus 2x2. Okay, 2x2. That's it. Now I will draw this table properly. You see, this is my table. Now this is my 0th iteration. So here I will put my iteration. That means I will calculate again and again. So this is my iteration. So my iteration, I will put it here. So I am going to draw the table like this. Now this is my iteration number 0, 1, 2, 3, 4, 5, 6, 7. You can continue many times, but you can stop at a moment where you are getting the same answers. You are getting the same answers continuously. If you are getting for 2 iteration, you are getting all the answers same, then you can stop. Then you can say that your algorithm is converged. Okay. Now initially I told you we will put x is equal to 0, x1 is equal to 0, x2 is equal to 0, and x3 is equal to 0. So I will put my solutions first. Okay, 0, 0, 0. Now for iteration 1 I am going to calculate. For iteration 1 I am going to calculate. How? I will use my x1. So my x1 equal to 0, x2 equal to 0, x3 equal to 0. So for iteration 1 I am going to calculate. How to calculate next x1, x1, x2 and x3. We have the equation. So we will use these equations. We will use these equations here and calculate. So what is my x1? It is 1 by 15 into 85 minus 3x2 plus 2x3. If I put this x1, x2, x3, everything 0, not x1 in this equation, there is no x1 in this equation. So next I will do the calculation for 1 by 10. It's 1 by 10 into 51 minus 2x minus z, right? Not z, actually 51 minus x1, there is no z, it's minus x3. And this is 1 by 8, I think 1 by 8 into 5 minus x1 plus 2 x2. So now I will put my here I will put this guy x2 is equal to 0 and x3 is equal to 0. Then what will be the answer? I will get it as 5.66. Then it become, I will write it again 1 by 15 into 85. So I will get this become 5.666. So I will write this here 5.666. Okay. Next x2 I will get 1 by 10 into 51 minus, you see, x1 is 0, x3 is 0. So that's it. So I will get here this answer as 5.1. Okay. So I will put here 5.1. 5.1. Now next I will use another color. Okay, I will use another color. Now this equation I will put x1 is equal to 0 and x2 is equal to 0. Okay, and these are all from the iteration 0, actually iteration 0, and we are finding iteration 1. So we will use all the values from iteration 0 to obtain the solutions in iteration 1. So we will use all the values from iteration 0 to obtain solutions in iteration 1. So here it's 1 by 8 into 5, that's it. So you will get it as 5 by 8, 0.625. So it's become 0.625. So you got the first iteration. Now what is your x? So I am going to draw a line here now. Now I got my x1, x2 and x3. So you see here, this is my x1, this is my x2 and this is my x3. Now I am going to calculate for iteration 2. I will use the same kanun or same formula. This is so 1 by 15 into 85 minus 3x2 plus 2x3, and this is 1 by 10 into 51 minus 2x1 minus x3, and this is 1 by 8 into 5 minus x1 plus 2x2. So here I will use the same formula. Now you should see what is happening. I will use this red color. So I am going to find x1. Okay, I am going to find x1. So to find x1 I need x2, but which x2 I will use? I will use this x2 and I will use this x3 from the previous iteration. You see here I will use these guys, and I will use these two, and I will find by using these two I will find in the next iteration. So this become 1 by 15 into 85 minus 3 into what is x2? x2 is 5.1 plus 2 into x3 is 0.625. So I will get something here. What is my answer? Let me check my answer here. Okay, so I will get it as 4.605. So I will write my answer here. It's 4.605. That's it. Okay, now I got this. Now I will proceed with the green color. I will use the green color. You see, I will use next this equation for finding x2. To find x2 you need x1, but you will take x1 from the previous iteration and you will take x3 from the previous iteration. Now you can calculate. It is 1 by 10 into 51 minus 2 into x1 is 5.1 minus x3 is 0.625. So I will get this answer as 3.904. So I will write it here, 3.904. So how I am finding? You can see I will use this x2 and I will use this guy and I will use these both and I will find my x2. That is, everything is coming from the previous iteration. Next we will see for this color. Okay, so it's 1 by 8 into 5 minus what is my x1? I will take from here. So it's x1 is 5.666 plus 2 into x2. What is my x2? I will take it from here, 0.625. So this become 1.192. Okay, so this become 1.192. So how this is find? You are using this value and you are using this value. So both are used and finding this equation, finding this value. Now you can proceed in the same way. If you proceed in the same way, what I am going to say is that you will use I will use a different color. You will use this value and this value, and you will be finally finding out by using this equation for x1. You can find for iteration 3 this become 5.045. Similarly, for x2 you can use another equations. For finding x2 you can use this value and you can use this value, and finally you can find this. You will get 4.05. and for finding x3 you can use from x1 and you can use from x2, and finally you can find it as 1.020. So you have to proceed like this. So this is the idea. So you will use the previous iteration and proceed. So if you solve like this, you will get this answer next 4.994. okay, I will use black color. So you will get here in the fourth iteration you will get 4.994, you will get here 3.99, and you will get here 1.003. next you will get here 5.002, 4.001 and 0.998. okay. Next iteration, in the sixth iteration, please note that in the sixth iteration here, in the sixth iteration, that's very important. In the sixth iteration you are getting it as 541, and again in the seventh iteration you are getting 541. So you see here that both are same. So if you continue like this, you have to do the calculation many times. Maybe sometimes it will converge in fourth iteration, sometimes it will converge in fifth iteration, but you see here the answers in 6 and 7, that means answers means the solution, 6 and 7 are same. So the algorithm means actually the set of procedures. Algorithm is set to be converged. So you are getting the answer now. So this is your answer. You see here your answer is 5, 4 and 1. So what is the answer? So you will get here x1 is equal to 5, x2 is equal to 4 and x3 is equal to 1. So this is the answer. So you are getting this answer in the 6th and 7th iterations. Okay, in the iterations. Okay, iterations. The answer in the 6th and 7th iterations are same. So the algorithm is said to be converged. So this is your answer. So this is your answer. So this is your answer. Okay. So we may see sometimes one more problem in the next lecture. Okay. I hope you understood the Jacobi iteration method. So you will use so in Jacobi iteration method, you will use I minus 1th iteration values. That means the values you obtained during I minus 1th iteration to obtain the solution at ith iteration. Okay. So this is the idea, don't forget this. So you will use all these values from I minus 1th to find ith iteration. That means you will use the values of 0 to find 1. You will use all values in iteration 0 to find the solution in iteration 1, and you will use all the values from 1 and you will obtain the 2, and from 2 you will find 3, and so on. You would continue. If the values are same, if value in I minus 1 and value that you are obtaining in I minus 1th iteration and ith iteration, if the values in ith iteration are same, you can stop. Okay, and you can find the solution. Okay, that is the idea in Jacobi iteration method. Okay.